Hello everyone. In today's video we are going to be talking about covalent bonds and covalent compounds. So many compounds do not form ionic bonds. These compounds contain two or more non-metallic atoms. For example, CO2 is made from two different non-metals, carbon and oxygen. Remember that ionic bonds were made from the combination of a metal and non-metal. Let's just put a little reminder for ourselves up there. Hello. There we go. Okay, so ionic bonds, autocorrect does not like ionic. Ionic bonds form between a metal and non-metal. Really got to turn that autocorrect off. Okay, non-metal. Now there is a type of bonding we don't discuss, and that's metals and metal bonds are usually metallic bonds. And they are of their own properties. We don't really discuss them very much. They're not very interesting to us. Also, they don't have very interesting naming rules, so we don't do anything with that. Okay, so covalent bonds, metals and non-metals. So we are or covalent bonds are only the non-metals. So we really are talking about on our periodic table, we are looking at this little section that is above the staircase. So if you ever see that staircase on the periodic table, most of these elements up here, those are considered the non-metals, and those are the ones that typically we're talking about. Sometimes these rules extend to the whole matrix if we are including, if they are combinations with these other elements up top. So sometimes, but some things like lead for example counts as a weak metal, and so typically it's only confusing if it's on the staircase. Anything that's above the staircase is definitely a non-metal, and I will typically choose for you to do the naming of the same types of compounds all the time. So I will choose ones that are pretty straightforward, hopefully. So two non-metallic elements combining to form covalent compounds, the compound contains at least two different types of atoms. A molecule is the smallest unit of a covalent compound. A molecule of a compound has different characteristic properties than the atoms which form it. So we were talking about something like carbon dioxide. Carbon dioxide is a little carbon atom, something like this, and then two oxygen atoms on it. And that combination of atoms can exist on its own as what we call a molecule. This is a little bit different from ionic compounds. Ionic compounds are typically crystalline, and a crystalline compound is an infinite repeating shape and pattern. So it might look like this, so maybe something like sodium chloride looks like this in a crystal, and it goes on forever, And so that's a crystal. And so ionic crystals, they typically don't have these molecular units. The crystal has to be treated as sort of like a big, forever repeating pattern, whereas covalent compounds have very discrete units that we call molecules. So we don't typically think of ionic salts as being molecular. So maybe I'll add that to our little definition up here. So ions and metals, ionic and metallic compounds are usually not treated as molecular. They are crystalline and have no smaller units. I'm just going to get rid of some of this. I think it's going to get confusing for someone who reads this without watching the video, so I'm going to get rid of that part. Okay, so this is the non-metals. All right, so the one example of a molecular compound is the diatomic elements. So these are interesting because the diatomic elements are molecular elements. That means that all the atoms are identical, but the atoms are arranged in molecules. They are diatomic molecules, so they are groupings of two atoms that are stuck together. So covalent bonds are used in the formation of diatomic molecules. A diatomic molecule is made up of two atoms of the same nonmetal, sharing a pair or pairs of electrons. The elements that form diatomic molecules are unstable in single atoms and combine almost instantaneously to form these stable molecules. There are 7. Sometimes it's easy to remember Hofbrinkel, which is a sort of name that you can say, Hofbrinkel. I've seen like some pictures of Hofbrinkel the clown, and they kind of do, it's usually some very frightening picture like this, where they kind of do a nose here, and I don't remember how they got the mouth, but there's sort of like Brinkle. And then I think you use the CL to be like an ear, and it's this sort of, maybe we move the N to be the other ear, and sort of like this is a smile, and I'll just sort of sketch in the smile. Hopefully this doesn't leave you with nightmares. Hofbrinkel. Hofbrinkel the clown. I don't know. I guess it just kind of sounds like a clown's name. And I just have this picture in my head of a clown. Every time I say the words Hofbrinkel, I always think of a crazy clown. It looks kind of like that. Hofbrinkel the clown. So maybe that'll help, or maybe that'll frighten you and haunt you. At least, well, any way it goes, that you remember that these are diatomic elements. So anytime you write them out, or anytime you're asked to present them, they must be treated as if they are diatomic, as if there are 2 of them. So you can't actually isolate a single hydrogen atom. You always are going to isolate 2 hydrogens that are stuck together, sort of like this. Those are, if I ever ask you, elemental hydrogen is combined with elemental oxygen, what I'm saying is that there is 2 hydrogens combining with 2 oxygens, and the oxygens are connected together by some sort of covalent bond or bonds, and they combine together to form water, which is a different combination. So they're not found separately. So for example, 2 hydrogen atoms form a diatomic molecule. 2 atoms of hydrogen share electrons to make a single molecule of hydrogen gas. The Bohr molecule for the hydrogen molecule is shown below. So here, remember that a Bohr model for hydrogen would look like this. So that's 1 hydrogen, but together as hydrogen gas, you would have to put 2 of them side by side, and then the electrons would become shared. And by sharing the electrons, we now have 2 electrons in this shell, 2 electrons, and in this shell we have 2 electrons, even though they're the same 2. And that is a full shell. And a full shell means stability. And we can do the same thing with all the other Hofbrinkels if we want to do, so a good challenge for yourself is to do something like fluorine, where you have 2 electrons, and then you have 1, 2, 3, 4, 5, 6, and 7 electrons. And if you can shrink that down so it's a little bit more manageable, I'm going to copy and paste that. And if I bring another one nearby, I'm going to just fix this a little bit. So here's my 7 electrons and 7 electrons. You can see why they must always be diatomic, because when we combine them together, they now have 2 8-electron shells. So this is 8 electrons now, and this one's 8 electrons. Even though we didn't actually add any electrons, we just combined them. So note the diatomic molecules are still classified as elements, even though they are molecules. While it may be strange for a molecule to be called an element rather than a compound, remember that diatomic molecules are made of only one kind of atom. And that's the definition for an element, is that it's made of one kind of atom. Okay, so let's look at some covalent compounds. Be sure you can recognize nonmetals and metals. Look at the periodic table. Nonmetals are on the right and metals are on the left, below the zigzag under boron. If there are 2 different nonmetal elements symbols in the chemical formula, you are dealing with binary covalent compounds, sometimes called binary molecular compounds. So here are some examples. Let's see if we can figure out which ones are the ionic and which ones are covalent. So now we have the periodic table out. This is essentially going to be the line we're looking for here. This is called the staircase. It goes this way down the periodic table, and anything on top of the staircase is typically treated as a non-metal. Not so sure about these new elements down here. Don't really, these ones here, those are brand new elements. They aren't really used for anything because they are so new, and they're also theoretical. They don't really exist for very long, so we can kind of ignore those ones. But any of these other ones, all of this stuff, these are all the non-metals. Now, we don't have to think about the noble gases because noble gases don't react. That's their property. But any of these other elements, those are ones we want to consider when we talk about these combinations. I suppose if I was really mean, I could kind of do a question about xenon maybe, but that's a different story. Okay, so that's what they mean when they're talking about these metals under boron, the zigzag line on boron. So let's look at CO. So CO is a carbon and an oxygen. Those are both above the staircase, so that makes it a covalent compound. Let's look at nitrogen and oxygen. So far, oxygen's good. Nitrogen is also right there, so that is also a covalent compound. Let's consider sodium and chlorine. Sodium's over here and chlorine's over here. Sodium counts as being under the staircase or to the left of the staircase. So that makes it ionic. And we covered it in our last lesson, so hopefully that also helps. Now this next one is the 3 elements, which we aren't necessarily have to cover, but we can cover it still. Oxygen. Now the interesting thing is that hydrogen technically counts as a non-metal. Hydrogen also, on some periodic tables, you'll even notice there's sort of a dashed line here, and there's a hydrogen right here, because hydrogen does count as a non-metal in a lot of cases. So if hydrogen counts as a non-metal, then the magnesium and a hydrogen together make a ionic compound, and a magnesium and an oxygen and a hydrogen together also makes an ionic compound. Okay, let's look at carbon and fluorine. Carbon and fluorine. Okay, so fluorine's right here, carbon's right here, both above, so covalent. And it's always a good idea before I start one of these examples to stop, do it yourself, and then come back and watch the rest of the video. Phosphorus and bromine also going to be covalent. Okay, so now that we know what's what, we have to learn how to draw some names for these. And naming is a little tricky. So for naming covalent compounds, you must memorize the following numeric prefixes. These are SI prefixes. These are known. These are used throughout the Système International, the international system of units. So all of these are established. Anytime you have the number 1, you can use the term mono. 2 is di, 3 is tri, 4 is tetra, as in a Tetra Pak, a 4-sided box. 5 is penta, as in pentagram. 6 is hexa, as in hexagon. 7 is hepta. 8 is octa, as in octopus. 9 is nona, and 10 is deca, as in a decade. So we memorize these prefixes, then we look at the formula and use the prefix to represent the subscripted number in the formula. We can omit mono, but only for the first element. So if you have something that also has a second element, and that element is only a 1, we have to put a mono there. We follow the prefix by the element name, and then we change the ending of the second element always to "ide." So let's look back at these first numbers. We have a carbon and an oxygen. They both have subscripts of 1. So their subscripts of 1 mean that we would use the term mono, except for first elements we don't have to write mono. So we're going to go right here and we're going to write carbon for the first element. It does not change. It will only change in terms of what we put in front of it. And the only exception is mono. We don't have to put mono in front of the element. You can write monocarbon monoxide, but it sounds kind of funny, and I would prefer you didn't. But now the oxygen, instead of writing oxygen, we want to write oxide, just like we did in the previous oxide. And now because there is a number, a subscript beside it, we're going to put mono there. So, and we don't usually put two O's side by side, so it becomes monoxide, carbon monoxide. And so now you know why we always use carbon monoxide, and you might even have a carbon monoxide detector in your house. Let's look at this nitrogen with this N2O5, which we also said was covalent. So again, we're going to be writing nitrogen, and the second element is oxygen, which we turn into oxide. And now we think about the prefixes. So there are two nitrogens, so that means we're going to put di for two nitrogens. And we're going to put we have to put something for the oxide, and it's 5. Well, that would be penta, and usually we avoid two alphabets side by side, so we're going to go pentoxide. So we don't put the two, no two vowels. And usually just kind of listen, like hear it out. Hopefully it makes sense just to listen, to say it out loud. Okay, so again, we're going to write the carbon and fluorine for this fifth one. We're going to ignore the other ones because we are not doing ionic in this lesson. And remember we're going to change that second letter to ide, second word to ide, so carbon fluoride. And now we go and look at the subscripts. Carbon, the first element, has a subscript of 1, but it's the first element, so we do not have to put mono. Fluorine has a subscript of 4. It has a subscript of 4, so we do want to put a prefix, and we want that prefix to be representing 4, so that would be the tetra. And that way, and fluorine doesn't start with a vowel, so we're just going to keep the whole thing. So tetrafluoride, carbon tetrafluoride. Okay, let's look at the phosphorus now. So we're going to write out phosphorus. We're going to write out bromide, and they should all be lowercase, bromide. And remember, it's always IDE. And now we look at prefixes. Phosphorus is a subscript of 1, but it's the first element, so we don't have to write mono. And the subscript of bromide is 3, so we're going to write tribromide. That's kind of got a nice ring to it. I like that one. All right, let's try naming these other two. Okay, a couple of these we've already done. So actually, we've done 3 of those already. Wow, that's pretty boring. Let's see if I can just cheat here and copy those. So I'm going to just paste those down here. And so we worked our way through these already. So here's the phosphorus triboride. And you know, this is the kind of the thing. The more and more of these that you do, the more prepared you'll be. And you'll find that they are only so many of these that you can even do. I believe there's even a practice page that I can send you to online that you can practice these if you want. All right, so we only have the phosphorus with the 3 oxygens beside it, so let's write that out. First one stays the same. Second word changes to ide. And now we look at the prefixes. There is a 2 for phosphorus, so that's going to be di. And there's a 3 for the oxide, so that one is going to be tri. And this is a weird one. We do keep the two together because otherwise it doesn't work out. So trioxide. It's just A's and O's that don't go together, I guess. Breaking my own rules right away. Now we could reverse the process. So here we have diphosphorus pentaoxide. So we know that phosphorus is a P, oxide is an O. Then we look at the prefix di, put a 2, penta, put a 5. I like this a lot better than ionic. There's no guessing here. You just follow what the words say. You do have to learn the prefixes, but once you know the prefixes, you can just go for it. So now, if you want to know which one's left and which one's right, well, the right one will always stay on the right, the left one stays on the left. If you have to guess, then it's always the one that's closest to fluorine on the periodic table that goes to the right. So you can check here. let's do that P and O. Here's P, here's O. So notice that O is closer to F, so that's why it goes second. If we do carbon monoxide, carbon and oxygen, oxygen's closer to fluorine, so that's the one that goes to the left. Okay, boron and sulfur. Well, sulfur is closer to fluorine, so the sulfur will be on the right. Okay, diphosphorus trioxide. So here we have, I like to think of it like, look at the elements first. So phosphorus, oxide, di means 2, tri means 3. Carbon oxide, so carbon oxide, but its carbon doesn't have a prefix, so we know it's 1, and di means 2. Tetra nitrogen deca oxide, that means nitrogen is a word I saw, oxide is a word I saw, tetra means 4, and deca means 10. What a strange compound. Sulfur trichloride, so sulfur and chlorine, no prefix means 1, trichloride means 3, and then we're done. So, we should probably practice here as well. One more time. Phosphorus and chlorine, so that's going to be phosphorus, chloride, and please pause so that you can do it yourself. And then we just need a prefix for that chloride, and we're going to say it's 6, so that's going to be hexachloride. Sulfur, and you can use pH if you want, or F, and oxygen is oxide. So we have no prefix for the sulfur because it's a 1, and we do have one for the oxygen because there's 2. The second word will always, always, always have a prefix. Nitrogen and oxide. We have 3 nitrogens, so that's tri, and we have 5 oxygens for the oxide, so we need to say pentoxide. Nitrogen, oxide, there are lots and lots of oxides, and there's no prefix for nitrogen, and there are 3 oxides, so it's trioxide. And then you're done. All right, so there will be a worksheet coming out for you to practice that. Here you can see some formulas. This is a naming sheet if you want to try sort of a flow rate. So you get a chemical and you say, all right, is the first element a metal? And if the first element is a metal, then you have to go down this path over here and you go down this way. So let's say, the same thing if we just put this one, right? So is the first element a metal? Yes, the first element is sodium, so we go to the left. Is the first element multivalent? Is it lead, iron, copper, tin? No? Okay, so then we go false. Look up the charges on the metal and non-metal. Make sure the charges add up to 0 by adding subscripts. Now we write their symbols and write their subscripts, and that's the end. Oh, I guess this would have been formulas from your names. Sorry, I should have given you a name here to start with. So let's say we had sodium chloride. So we would look up the charges on the metal and non-metal. This would be sodium plus, and the chlorine would be the charge. And we do the crisscross, and then simplify if we have to, and we get our formula, sodium chloride. If we are given something that's non-metal, so if we get diboron trioxide, we find out boron is not a metal. So we go this way. That makes it covalent. The second one is oxide, but all we need to do is convert the prefixes into subscripts after the symbol. So this is a prefix of 2, this one's a prefix of 3, so we're going to write boron 2, oxygen 3, just like that. All right, so hopefully that helps you out, and there is another sheet that we're missing, which is weird. There's a reverse version of this, but I guess you can just start at the bottom and work your way back up if you want, if that helps. I think that the reverse is a little bit more complicated. All right, good luck, and we will talk to you in the next video.